Hello, everyone, and welcome to another exciting rendition of physics problems done for review with Mr. Levy. So today we are going to be working on the multiple choice and short answer problems that I gave you to review for the test that we're going to have on Tuesday. So if you don't have the handout still, or you forgot it at home or at school, or you just don't know where it is, for before each problem, pause, try the problem, and then I'll go over the answer. So here we go. Consider a uniform hoop of radius r and mass m rolling without slipping. Which is larger, its translational kinetic energy or its rotational kinetic energy? So if you recall, a hoop with radius r and mass m, for the rotational kinetic energy, you have k rotational, which is equal to 1/2 I omega squared. And then for the translational or the linear kinetic energy, you have 1/2 mv squared. And so the question is, which one of these is bigger? What we need to do is we need to find a way to express one in terms of the other. So, for example, this has I omega and this has mv. So we either need to find a way to get this to just be mv, or we need to find a way for this to be I omega. The easier one would obviously be converting this. So we can write in the moment of inertia for a hoop, which is just mr squared. And we can convert this to your favorite, v over r. Now remember, just because there is an omega here does not mean you always have to convert to v over r, okay? Only do it if you need to combine linear and kinetic energies. If it gives you omega in the problem, don't make your knee-jerk reaction to convert omega to v over r. It's not always necessary. This time, however, it is. So we convert this to v over r squared, which becomes 1/2 mr squared times v squared over r squared. Noticing that we can cancel out these r's, we get this, which is just equal to 1/2 mv squared. And would you look at that? These actually have the same value, so our correct answer is A. They are both equal. Two uniform solid balls, one of radius r and mass m, the other of radius 2r and mass 8m, roll down a high incline. They start together from rest at the top of the incline. Which one will reach the bottom of the incline first? So we're looking at time here. So what we can do is we can consider this from an energy standpoint. So if we look at our situation here, you've got the two balls starting at the top of an incline and rolling down. Now if we look at our energy bar chart, which we should make for this, what we see is that you've got gravitational potential energy to start, and we have kinetic rotational at the bottom because it's going to be rolling, but the center of mass of our ball will also be moving forward with some linear velocity as well. So it is rotating this way, but it is also moving this way. Only in this situation does it have both rotational and linear kinetic energies, okay? If it is something that is just rotating, like, for example, the rod in our momentum problem, where it's just a swinging rod that swung back and forth, that does not have any linear velocity because it is not moving, the center of mass of it is not moving in a line. The whole thing is rotating. So here's our gravitational potential energy and our kinetic, linear, and rotational. Sorry about they're not even, but pretend this is two blocks, this is only one. Alright, so up here we've got our UG, which is mgh, and then this is just equal to 1/2 I omega squared plus 1/2 mv squared. Now, if you're clever, you'll realize that the very end is only going to be in terms of g and h, regardless of the fact that there's all these m's and r's in the middle here. But just to make sure, let's do some of the math. So for the first one, let's take the one that is the 2r and 8m. So for 2r and 8m, the m is now going to be 8m here, gh, which is the same for both, and that's equal to 1/2 I omega squared. I, for a solid sphere, which is what these solid balls are, is 2/5 mr squared. In a real test, I would give you this in the problem. Because this is a practice, you have the opportunity to look it up yourself. So this 1/2 times 2/5 m, which is 8m, and r, which is 2r. Remember, the coefficient in front of the r goes inside the parentheses. This whole thing is squared. Plus our kinetic energy equation, which is 1/2 m, which is 8m again, and v squared. So much like the previous problem, we're going to... Oh, I forgot an omega in here. Sorry about that. Times omega squared. There we go. So this is I omega squared. So this is I, here's your omega. So we're going to convert this into either all m's or all omegas. Either one is fine. I'm going to convert it to v. Because what we're doing here, remember, we're trying to figure out which one hits the bottom first. So if we find out which one has a bigger velocity at the bottom, or if they have the same velocity at the bottom, we'll know which one would have gone to the bottom first because of the acceleration. The one that had more acceleration will hit the bottom first. So we can rewrite omega as your favorite v over r. And we can also start canceling some stuff out. For example, you'll notice that there's this 8m that's consistent throughout, so we can cancel that out. We can cancel out these 2's here, so we make this just 1/5. So we've got GH is equal to 1/5 to, where am I? 1/5 for r squared, because it's 2r squared, times omega squared, which is v over r squared, plus 1/2 v squared. Distributing the square, this becomes v squared, and this becomes r squared, and this r squared cancels out this r squared, so this goes away, and we're left with just GH is equal to 4/5 v squared plus 1/2 v squared. I'm going to leave this here because, well, if we need to later, we can find out which one has the higher velocity. Because if we end up with this same equation for our other one, then we know that will be fine. And if you realize, there's no r's or m's here. All the r's and m's got canceled out, regardless of any coefficient in front of it. So really, we don't actually have to keep going. If you need to prove to yourself, you would do the same thing here that we did with this one, only instead of 8m, you just have m, and instead of 2r, you have r. But realizing here that there's no function of m or r tells us that they will both actually have the same velocity when they reach the bottom, which means that their acceleration was the same, which means that the time they took to get to the bottom was the same. If you figure this is our displacement, right? Delta x. And if you think about our equation, x final is equal to x initial plus v initial t, which is 0 for both of them, plus 1/2 at squared, right? T is going to be a function of the square root of 2 delta x over a. Yes. And since our a here is we could figure out the a based on the velocities, the initial and final velocities. And if they have the same velocity when they reach the bottom, their acceleration was the same because they reached that velocity in the same distance. So the correct answer here is they both reach the bottom at the same time. Moving on. All right, next one. A ballet dancer is spinning in the middle of a horizontal frictionless stage. It's a weird place for a ballet dancer to be. Which of the following things could he change by moving parts of his body or his whole body? There could be more than one correct. So let's take a look at these one at a time, and we'll go and see which one we agree with and which one we don't. So A, the location of a center of mass or center of gravity. This is absolutely reasonable because your center of gravity or your center of mass has to do with your essentially mass distribution. So if he is standing with his arms out to his sides or whatever doing the spin, and then he simply spreads out, there's a leg, there's an arm, whatever, then his center of mass, which was probably here somewhere now, is now over here. So it would be very easy for him to change his center of mass. So this one is possible. His rotational kinetic energy. Obviously, if you remember that when I sat in the chair and I had the weights in my hands, and I had them out and then brought them in, then I went faster, right? So my rotational kinetic energy is obviously changeable. His angular momentum, by simply moving parts of his body, he is able to sort of swing himself around. So he's actually able to do some sort of angular impulse on himself, just by moving parts of his body. So his angular momentum is possible to change. His moment of inertia is obviously changeable. Going from here to here is already changing moment of inertia. If you recall, moment of inertia is the sum of mr squareds. So if it is the sum of mr squareds, then if you change either m or r, then you can easily change your moment of inertia. The next, so D is possible. E, the horizontal component of his linear momentum. So he was standing still, spinning on stage, and then he needs to move either this way or this way. Well, if it is a frictionless stage, it is not possible for him to actually have something exert a force on him to change his horizontal component of his linear momentum, right? His angular momentum he can change by swinging his legs around, because his muscles in that system are capable of causing an impulse, exerting torque on the system. But here, there is no force. If it is a frictionless stage, there's no force that can be exerted on him to change his horizontal component of his linear momentum. So this one's out. His translational kinetic energy, it is possible to go from a spin to a linear sort of leap, by just extending out his body. So this one is possible without pushing, sort of like this. And then finally, his total kinetic energy, which on the AP is just the combination of linear and rotational. So this is actually also possible. So everything but E is possible in this problem. Moving on. Spinning ice skater on extremely smooth ice is able to control the rate at which she rotates by pulling in her arms. Which of the following statements are true about the skater during the process? There could be more than one answer. She is subject to a constant non-zero torque. Her kinetic energy remains constant. Her angular momentum remains constant. Her moment of inertia remains constant. So immediately we can know that this can't be true, because if she pulls in her arms, then her moment of inertia is changing by definition. She is subject to a constant non-zero torque. If that were the case, then she would be speeding up, which she is not. So this one is out. Her kinetic energy remains constant, or her angular momentum remains constant. So if you recall, again, when I was sitting in the chair and I had my arms out and pulled them in, I started to spin faster. So by definition, the kinetic energy cannot be the same. Her angular momentum, however, will be the same. So the correct answer here is C. When is the angular momentum of a system constant? Only when no net external torque acts on the system or is exerted on the system. Only when its total kinetic energy is constant. Only when the moment of inertia is constant. Only when no net external forces act on the system. Only when the linear momentum and the energy are constant. So this one, B, does not change, or it does not affect it, because the kinetic energy doesn't affect the momentum. We often find actually that in inelastic collisions, if there are one, the kinetic energy will not be constant, but the momentum will. So that's out. When the moment of inertia is constant, we don't need that either. Again, I refer you to me sitting in the spinning chair with the weights. Only when no external forces act on the system. There can be external forces being exerted on the system, but they have to be of a special kind to cause a change in angular momentum. You'll see where I'm getting with that. So that's out. Only when the linear momentum and energy are constant. Again, if the energy doesn't have to be constant, then both of these don't have to be constant. Oftentimes, linear momentum will not be any linear momentum before, and there might be some after, but angular momentum can still stay the same. So really the only thing is only when no external torque acts on the system. What is the angular speed in radians per second of a flywheel turning at 813 RPMs? So RPMs means rounds per minute, okay, or rotations per minute. And so we need to convert rotations per minute to radians per second. If you recall, one rotation is 2 pi radians. Okay, you should know that from math. And then converting from minutes to seconds, 1 minute is 60 seconds. So if we take our RPMs, which is 813, multiply this by 2 pi divided by 60, we will get our solution, which is roughly 85.14 radians per second. Two uniform solid spheres have the same mass, but one has twice the radius of the other. The ratio of the larger sphere's moment of inertia about a central axis to that of the smaller sphere is, so effectively what we're looking for is I big over I small. All right, since these are solid spheres, I mentioned it before, their moment of inertia is 2/5 m r squared. In this case, r is twice the radius of the others, so we'll call this 2r squared. And here we will have the ratio of the larger sphere's moment of inertia to the smaller. So we have the smaller one, so it's going to have the same setup, same mass, only this time it is just r squared. Converting everything here, or canceling out, 2/5 go away, m's go away, the r squareds go away, and all we're left with is 4/1. So the correct answer is B. Initially, a small 2-kilogram rock is whirling at the end of a very thin string in a circular path of a radius 0.75 meters on a horizontal frictionless surface, as shown in the figure. So it's like a tetherball type thing. The initial tangential speed of the rock is 5 meters per second. So if it's going, I guess it will be spinning this way. This would be 5 meters per second. And a few seconds later, the length of the string, which was originally 0.75, goes down to 0.25 meters. So the string has been slowly winding around the vertical rod, and a few seconds later the length of the string has shortened to 0.25 meters. What is the instantaneous speed of the mass at the moment the string reaches 0.25 meters? So as soon as radius is 0.25, what is our new tangential velocity? So not rotational. So what we have to do first is, this is going to be a momentum problem because momentum is going to stay constant for this problem. So we have I initial omega initial is equal to I final omega final. So we know our initial tangential velocity, so we have to be able to plug tangential velocity into here. So that is going to be, again, our favorite, V over R initial and initial. Right, and now you might want to say, because it is a rock or a ball, that this is 2/5 mr squared. But what it is actually an object rotating around a central point. So if our axis of rotation is here, and this thing is going around the center of rotation, this is actually just the moment of inertia for a point particle, which is just mr squared. So I here is just going to be mr initial squared, and then I final omega final is just going to be mr final squared times V final over R final. So if you want to solve things out algebraically, these r's will cancel out, leaving us with mr initial, V initial here, and then over here the same thing, the R2 R finals cancel out, so you've got mr final, V final. And what we are solving for is the speed of the mass at the moment the string reaches the length 0.25 meters. So we're looking for V final. So I'm just going to, cancel out m's because the n doesn't change, and divide both sides by by R final, excuse me. So V final is going to be equal to R initial V initial over R final, which is going to give us a solution of, if you plug everything in, 15 meters per second. And we want to make sure that it is faster, because if you've ever played tetherball, you'll know that as this wraps around, it will start getting faster and faster, because that angular momentum was conserved, right? All right, moving right along. 3 solid uniform cylindrical flywheels, each of mass 65 kilograms and radius 1.47 meters, rotate independently around a common axis through their centers. 2 of the flywheels rotate in one direction at 8.94 radians per second, but the other one rotates in the opposite direction at 3.42 radians per second. Calculate the magnitude of the net angular momentum of the system. So what this means is you've got 3 flywheels rotating about the same axis. And the 3 flywheels are effectively the same, except for the fact that one of them is spinning in the opposite direction. Pardon my terrible art here. Right? So imagine these are 3 wheels. I know it's kind of hard to do. Ugh, that's gross. So 2 of these are spinning with an omega, let's say this way, just for fun, of 8.94 radians per second. This one and this one. But this one is spinning up in the opposite direction of the other 2 at 3.42 radians per second. Alright, so, and we want to find the angular momentum of the entire system. So what we're going to do is simply add up all the angular momenta for the whole system. So we've got I, well really we've got I, if we call this 1, 2, and 3, we have not I, but actually L1 and L2, which are both going to, L1 and 3, right, which are both going to have the same momentum. So we'll just call this twice that one, angular momentum, plus the other one, L2. But because L2 is spinning in the opposite direction, much like torque, we can call 2 of these positive and 1 of them negative to indicate that they're in opposite directions. So let's call this one negative, just for fun. And now this is just a matter of plugging stuff in. So 2I omega plus, or minus, I guess, I, so this is I1 or 3 omega plus I2 omega. And if you want to simplify, you can realize that they all have the same I, and that doesn't change, it's just omega that changes. So this is just going to be I times 2 omega 1 and 3 minus, minus omega 2, which is what this is. Alright, and plugging all those values in, solving for I, which for a solid sphere is going to be 1/2 mr squared. Plugging that in here, plugging in the different omegas here, will give us a total angular momentum of D, which is 1020 kilograms meters squared per second, roughly. Alright, moving on. This is the last of the multiple choice. A uniform 135 gram meter stick rotates about an axis perpendicular to the stick passing through its center with an angular speed of 3.5 radians per second. What is the magnitude of the angular momentum of the stick? So again, reading that one more time, a uniform 135 gram meter stick rotates about an axis perpendicular to the stick passing through its center. In other words, this is just a meter stick rotating about the center here. So this whole thing is 1 meter. This is obviously 0.5 meters, 1 meter. So the question is, what is the magnitude of the angular momentum? And we're given omega here, we're given the mass here in grams, and we know the length, obviously, which is 1 meter. Looking it up, the moment of inertia for a bar, for a rotating about its center, is 1/12 mr squared. So our angular momentum, L, is going to be I omega, which I is going to be 1/12 m, which is 135 grams or 0.135 kilograms, times, now in this case, it's not r, it's actually, well, we can call this r, but really it's actually L, the length of the stick. So this should actually be an L here, not an r. Okay, and this length is not the length from the center of mass, from the center of rotation. This is actually the length of the entire rod. This is specific to a straight rod spinning in a circle around its axis, a thin rod specifically. So this is going to be L, which is 1, obviously, squared, times omega, which is 3.5 radians per second. All right, and once you go through all that math, you will find that the answer is E, 0.0394 kilograms meters squared per second. All right, so we're going to move on to the open-ended problems. A 24.5 kilogram child is standing on the outer edge of a horizontal merry-go-round that has a moment of inertia of blah about a vertical axis through its center and a radius of 2.4 meters. The entire system, including the child, is initially rotating at 0.18 revolutions per second. Okay, so revolutions per second is not the right unit, so we're going to have to convert that later. I'm also going to underline some of the other important information here. So this is the moment of inertia of the merry-go-round, and it's got a radius r of 2.4 meters. Find the angular velocity of the child if the child moves to a new position 1.1 meters from the center of the merry-go-round. So instead of being at the 2.4 meters where the child starts out, it moves into 1.1 meter from the center of the merry-go-round. So we're going to start off with a picture, obviously. So this is our merry-go-round. Here is our child over at the outer edge. This is our initial radius of 2.4 meters. And we know that the merry-go-round has an I of 989. This is just the merry-go-round, 989 kilograms meters squared. That means we do have to find the moment of inertia for the child later. And we've got our frequency essentially, which is 1.18 revolutions per second. We need to convert that to our actual omega angular velocity of radians per second. So let's do that quickly. So we know that if it is 0.180 revolutions per second times 1 revolution is 2 pi radians, then doing 0.18 times 2 pi, so multiplying 0.18 times 2 pi will give us 1.13 about radians per second for our omega. So this omega is 1.13 radians per second. All right, and then afterwards, so this is initially, and then finally, the child moves to a smaller 1.1 meters, I believe, right? Yep. The radius of our merry-go-round is still 2.4, and the I is still 989 kilograms meters squared. But now the added moment of inertia of the child is going to be different. So setting up our equation, we've got essentially a conservation or constant angular momentum here. So because there's been no torque or anything, the angular momentum initial is equal to angular momentum final, which means that I omega initial, or total I, so sum of the I omega initial is equal to sum of I omega final. Now, in our system with the child and the merry-go-round, we have two different I's, right? We've got I of the merry-go-round, which we're given numerically, plus the I of the child. Since the child is just, we'll consider a single point, this is just going to be I child, where I child is just the mass of the child times his location on the merry-go-round squared. So the moment of inertia of a point particle. This is going to be times omega initial, and this is going to be the same, well, almost the same. The I of the merry-go-round is going to stay the same, but I final for the child is going to be different. Times omega final, which is what we're solving for. So, we are looking for omega final of both the child and the merry-go-round, since they will have the same omega final. So I'm going to move up here. Omega final is equal to IM plus IC initial times omega initial over I merry-go-round plus I child final. Our initial, well, and so this equation here, let's solve that so that we can just plug in numbers. Mr squared, right, the mass of the child is 24.5 kilograms, so we got 24.5 kilograms, times the initial radius, which is going to be 2.4 because he's at the edge of the merry-go-round, meters squared. So our initial I is going to be 141 kilograms meters squared. And then our final I is going to be, so this is I initial, I child final is going to be the same mass, 24.5 kilograms, but at the new location, which is 1.1 meters squared, which is going to be 29 point, we'll call 29.6 roughly kilograms meters squared. All right, so plugging in here, we've got IM initial, which is just 989 kilograms meters squared, plus our initial angular momentum of the child, which is this 141 we had up here. This is our I child final. So plus 29.6 no, sorry, excuse me, plus this is 141, this is the initial. I should have said something. 141 kilograms meters squared times our initial omega, which is over here, 1.13 radians per second. Sorry, it's getting so cramped. All over our final, the angular moment of inertia for the merry-go-round, which is still 989 kilograms meters squared, plus our final angular moment of inertia for the child, which is 29.6. And going through that whole mess through your calculator, we end up with a solution of 0.2 revolutions per second, which is the solution given in the back, which you can convert from, you're going to get this in radians per second, obviously, and then you would have to convert that from radians to revolutions per second. I would take both of those as a solution, although I'm not sure why they gave that as a solution here. But just convert it, it's fine. And so right now I'm going to take a break. This video is getting very long, and I will continue and do the rest of these 4 problems in a separate video. I just want to get at least this part uploaded for now so that you can start, even though I'm sure all of you are just going to look at this later tonight, but I do what I can. So to be continued in the next video.